we can solve this weight vector and create the hyperplane equations considering this weight vector. We must discover the values of this a here. Since we have this weight vector omega here, we can substitute the values of this point, and also in using this point we can substitute these two values here. When we place the equation g using the input vector 1 times 1, we know that we have the value -1 because it belongs to the class circle. So we will have this value here. When we use the second point and we apply the function, we know that it will deliver the value 1. So we substitute here in the equation also. Well, given these two equations, we can isolate the value of omega 0 here. In the second equation, we will have omega 0 equal to 1 minus 8 times a. So, using this value, we put omega 0 in this first equation, and we will reach the value of a, which is 2 divided by 5. Now we discovered the value of a, and now we will substitute in the first equation and also discover the value of omega 0. So by dividing here, we will come to the conclusion that omega 0 is minus 11 divided by 5. And since we know that the weight factor is a and 2a, we can substitute the value of a here. And will deliver these values of the weight vector. So in this case, these are called the support vectors. Because they compose the omega value, 2 divided by 5 and 4 divided by 5. When we substitute here the values of omega 2 divided by 5 and 4 divided by 5, and also the omega 0 value, we will deliver the final equation, which defines this hyperplane, this green hyperplane, which is x1 plus 2 times x2 minus 5.5. And this hyperplane classify the elements used in support vector machines. These are the value of z2 is this hyperplane. We have, in the case of the red hyperplane, we have this distance, so this is the margin which we represent by z1, and in the case of the green hyperplane, we have the margin choice will be the green. This hyperplane is defined by one equation. We can state this equation as this one. We have a one hyperplane for all the input vectors which belongs to class 1, in this case the circles. And also we scale this hyperplane so that it will deliver values smaller than -1 for all values which belongs
Water?
Yeah, water.
Well, we only serve paying customers, so you'll have to order more than water. If you're broke, go somewhere else.
50 dumplings. Is it a deal?
Huh?
You feed me, and I'll take care of those guys for you.
But,
So far we've discussed L2 regularized logistic regression, and we briefly mentioned what happens when you have L1 regularized logistic regression. Let's talk about it in a little bit more detail. Unlike in the regression course, we're not going to derive the learning algorithm for L1 regularized logistic regression. It's going to be the similar thing to what you did with Lasso. We're just going to show kind of the impact it has on our data, on our learned models. So recall the notion of sparsity. So a model is sparse when many of those WJs are equal to 0. And that can help us with both efficiency and interpretability of the models, as we saw in regression. So for example, let's say that we have a lot of data and a lot of features. So the number of Ws that you have can say be 100 billion. 100 billion possible values. This can happen in practice in all sorts of settings. For example, many of the spam filters out there have hundreds of billions of parameters in there, or coefficients that they learn from data. So this has a couple problems. It can be expensive to make a prediction. You have to go through 100 billion values. However, if I have a sparse solution where many of these W's are actually equal to 0, then when I'm trying to make a prediction, so I'm trying to compute the sign of Wj times the feature Hj of xi, I only have to look at the no-zero coefficients Wj. Everything else can be ignored. So if I have 100 billion coefficients, but only say 100,000 of those are non-zero, then it's going to be much faster to make a prediction. This makes a huge difference in practice. The other impact the sparsity has, having many zero coefficients being 0, is that it can help you interpret the non-zero coefficients. So you can look at the small number of non-zero coefficients and try to make an interpretation. Oh, this is why a prediction gets made. And such interpretations can be useful in practice in many ways. So how would you learn logistic regression classifier with sparsity in it, sparsity inducing penalty? So what we do is we take the same log likelihood function, LW, but we add extra L1 penalty, which is the sum of the absolute value of W0, the absolute value of W1, all the way to the absolute value of WD. So by just changing the squares, sum of squares to be sum of absolute values, we go into what's called L1 regularized logistic regression, which gives you sparse solutions. So that small change leads to sparse solutions. So just like we did with L2 regularization, here we're also going to have a parameter, lambda, which controls how much regularization we introduce, so how much penalty we introduce. And the objective becomes the log likelihood of data minus lambda times the sum of these absolute values, the L1 penalty. When lambda equals to 0, we have no regularization, which leads us to the standard MLE solution. Just like we had in the case of L2 regularization. Now, when lambda is equal to infinity, we have only penalty, so all weight is on regularization, and that's going to lead to W hat being everything 0, all 0 coefficients. Now, the case that we really care about was when lambda is somewhere between 0 and infinity, which leads to what are called sparse solutions, where some Wj's are not going to be equal to 0, but hopefully many other Wj's, and this is our estimate, so Wj hats are going to be exactly 0. So that's what we're going to try to aim for. So let's revisit those coefficient paths. And here I'm showing the coefficient paths with L2 penalty. You see that when the lambda parameter is low, you have large coefficients learned. And when the lambda parameters gets larger, you get smaller coefficients. So they go from large to small, but they're never exactly 0. So the coefficients never become exactly 0. If you look, however, at the coefficient paths when the regularization is L1, we get something much more interesting. So for example, in the beginning, the coefficient of the smiley face, oops, that should be frowny, that should be, coefficients never become exactly 0. If you look, however, large to small, but the lambda parameters get slightly 0. Smiley face is 0. So the coefficients never become exactly 0. If you look, however, at the coefficient paths when the regularization is L1, we get something much more interesting. So for example, in the beginning, the coefficient of the smiley face, oops, that should be frowny, that should be smiley face, has a large positive value, but eventually becomes exactly 0 from here on. And similarly, the coefficient for the frowning case, for the frowning face, is a large negative value, but eventually over here, the frowning face has a coefficient that becomes 0. And so it goes from large all the way to exactly 0. And we see that for many of the other words. So for example, in the beginning, the coefficient of the word hate is pretty high, and that's a pretty important word. But around here, hate becomes irrelevant. And so it's just a quick reminder. These are product reviews, and try to figure out whether it's a positive or negative review for the product. And we can look at what coefficient stays non-zero for the longest time. And this is exactly this line over here, where it never kind of hits 0, never stays exactly 0. And this is the coefficient of the word disappointed. So you might be disappointed to learn that frowny face is not the one that becomes 0. But in the beginning, disappointed is not as, the coefficient is not as large, so it's not as significant as frowny face, but it's the one that stays negative for the longest. And so frowny face is not, it might be disappointed, so frowny face is not as important as disappointed. And disappointed, probably because it's prevalent in more reviews, and when you say disappointed, you're really like in a negative review. That coefficient goes on for a long time. So you see these transitions. So the coefficients of those small numbers like your views goes to 0 early on. Smiley face lasts for a while and then becomes 0. Frowny face lasts for longer and then becomes exactly 0. But for sufficiently large lambdas, all of those are 0 except for the coefficient of disappointment.